Hello.
Even computers have Monday mornings. Okay, I'll go on. Yeah. So the problem, of course, is that this is divergent, and we interpret that as simply there being more partonic scatterings, more than one partonic scattering in each event. So if you include some cutoffs saying that I'm only interested in jets above some type GV, you will find that this exceeds the total cross-section. And when it does, you basically say that, well, you can get the number of hard scatterings by integrating this cross-section from some lower limit and just dividing out the total, in this case, it's semi-inclusive, non-diffractive cross-section. So basically, you could start by saying, oh, look, I will have 3.5, and you assume that it's a normal probability distribution, and you can draw a number that on the average is 2.5. And for each of these, you generate the hard scattering and parton showers and stuff like that. What? That's the average amount of hard scatterings per nuclear collision. Yeah. Okay, so I'm going to describe how this is done in Pythia, which is actually the first implementation of anything like this. First of all, Pythia tries to treat everything as perturbative. So rather than introducing a cut, it introduces some kind of soft cutoff. So you have put in a soft scale in the alpha S and a soft scale in the denominator. So this takes out the KT to the fourth here. This takes out the alpha S in this guy. So if you have a dampening factor for small KT, you get something like this. This KT here, you can motivate it with things like color screening. If there is a lot of gluons around, they will start to self-interact, and there will be what we call recombination and sharing and things like that, saturation. But again, this is a parameter. We know what it is. It's a parameter, and we're going to toy around with it. And it was fairly soon realized that this parameter probably depends on the center of mass energy of the scattering. And the parameterization of the parameter looks like this, where you have the energy to the power of epsilon, which is around 0.8, which with some hand waving, you can actually relate to the increase of the total cross section, which also increases like S or the energy times a factor like this. So this is what we do. So we have one more thing to fix. We need to know the non-diffractive cross-section, and that has been measured. And so you can just put it in from measurements. Donachie and Lansoff have made many nice parameterizations of this, and there's also other people who made parameterizations. So you get this number from somewhere. You tune the lower, the soft turnoff of the cross section, and you get this. However, you also need to think about that some collisions are more central than others. Some are just peripheral, they just graze each other. So there is some kind of overlap function you need to take into account, because the parton densities in what we had before, which is in there, assumes you integrate over everything. So in principle, you will have some kind of parton luminosity function that depends on x1 and x2 on the impact parameter between the two protons. And this can be assumed to factorize more or less, so that it is the product of the two parton densities times some overlap function, which we can calculate if we know the density in space of a proton, because of how much was the overlap in space-time. And then this rho is a matter distribution in a proton, and we know approximately what it looks like. It should be something like a Gaussian. Everything is a Gaussian. But you can toy around. You can have some X dependence in it, because we know that that there are a lot of more particles around when you have small x.
The first extract the harvest interaction, and then you select an impact parameter because in any case interested in efficient in generating events in which you have something out effect, because basically to those decided to first select an impact parameter and then.
Yeah, it is true. And we do that also sometimes. This is a bit technical. I think I'll come to this fairly soon. No, I didn't. But as you said, in Pythia, we like to order stuff, because if you can order stuff, we can use this nice Vito algorithm I talked to you about yesterday. I like that. So ordering stuff is good. And you do expect, it's physics, of course, that something that has a very high scale happens in some sense first, right? So what is actually done in Pythia is first you generate inclusively the hardest scattering without this overlap function, just the normal cross section. You throw out that, you add a no scattering probability. So it's not only a hard scattering, it is the hardest so far. So it's a probability of the cross-section we had before times the integral over e to the minus the integral over all pt's above. So this is get the right probability to generate the hardest. And once you've done that, then you kind of undo this to say that, well, this hardest was actually not so hard. And if you go around these equations, you can then generate a likely impact parameter for a collision where I get the hardest PT of 33 GeV or 5 or whatever. So that is what is actually done in Pythia. Now, before I go on, I need to talk a bit about scales. Because it's important, hard scales, where we are. And if we look at what can happen at the LHC, we have, of course, a total center of mass energy, 13 TeV, squared. We have the partonic center of mass energies, partonic scattering, which we call S hat. And we have the transverse momentum, or in general, the T hat, the exchange momentum inside the hard scattering. And we have down to lambda QCD, which is where perturbation theory goes away. And we can have other stuff like the mass of the Higgs, mass of the. And the thing is that every time you have large separations of scales, you will have to worry about large logarithms. So we've seen before that if you have a very high KT compared to lambda QCD, you need to resum the things we resum in a Parton shower. We call it D-Glap evolution. But you also have the fact that this KT in turn can be very, very much smaller than the total center of mass energy. That also gives you logarithms, which can be resummed. And we have other names here. The L is the same in these two, that's Lipopov. But BFKL, CCFM is another way to resum this. And we can even have KTs which are much smaller than the hard scattering energy, and that's FKL. And you can think about having at the coming FCC, 100 TeV-S, you can have a TeV-S hat where you have W produced with a very large PT. And then you really have to worry about 4 or 5 different scales in the same event that needs to be treated. So it's things, right? So if we're talking about very small PT, and if you think about what Pythia does, it just says, oh, well, it's like any hard scattering. So we can use D-Glap evolution. But really, we should be worrying about BFKL resummation. And Pythia doesn't do that directly. It has things that includes the same effects, but it's not done correctly like the Russians or BFKL would have liked us to do. Malitsky, Fadin, Kuryaev, Lipatov. So basically, Pythia does this, which is hard scattering, but we should actually worry about the whole cut Pomeron here, soft, and that is not done properly in Pythia. So for very small x, small KT, we also have this saturation thing, which is basically where we don't only have gluon splitting, we also have gluon recombination, also not in Pythia. But there are other things in Pythia that are important. Energy momentum conservation. It's important. It's not only important because nature demands it, but actually, if you're writing an event generator, you have some cross checks that you always do. You always conserve energy momentum. So you can always go and look at an event. Is momentum not conserved, then there is a bug because every step should conserve energy momentum. This is also why we like pseudo-random numbers that have the same sequence every time we run the program, so that if you in event 4,300,043, there is energy momentum conservation is gone, right? So we need to understand why, and to get that in the debugger, we have to be able to reconstruct the random number sequence. Beside the point, sorry. What happens when we have the soft things that actually takes quite a lot of energy out of the proton in the end? That means these multiple scatterings, they are not independent. Because if we take out momentum, there will be less momentum for another one. So we not complete independence of these things. One could have it just emit until you run out of momentum. Or you can rescale the PDFs after each multiple interaction. And that's actually quite tricky because you have to take into account flavor conservation or stuff like that. And then you realize that also initial state showers takes momentum from the proton. So we need to worry about now. If you just look at the scales, you would say that it's natural if you have one collision, it's natural to have initial state first, then final state, and then hadronization. But what are we going to do now? Should we generate all the multiple scatterings first and then shower initial state and final state? Or shall we, after each multiple scattering, generate a shower? Because that will also take momentum out of things. And we must ask ourselves, is it reasonable that low PT multiple scattering takes out so much momentum of the proton that there is a high PT shower emission in the initial state that cannot be done? So we need to order this, and the way it's done in Pythia is actually to include these multiple scatterings in the shower procedure. And this is what it looks like. So you have the primary scattering. This is the one that we generate with the full PDFs, and then we calculate this impact parameter and we get this overlap function. So after this scattering, we start the shower process. So we can have an initial state shower splitting, we can have final state shower splitting, but we can also have an additional multiple interaction. So we let them compete and say that, well, whichever of you comes up with the hardest thing, you get to go first. And again, we have this beauty of ordering that the no emission probability exponentiates and factorizes for each channel. There is a rescattering of final state partners that is turned off by default, but you can include it if you want. So what you do is you just ask a final state shower. Okay, so what do you want to do next? Oh, I want to do this. Give me a KT. And then you have the final state shower. So, oh, I will split the glue on here at another KT. And then multiple interaction generates a possible new scattering at some PT. And we just pick the one that is hardest. And then we continue and continue and continue. In this way, we let them compete. And the idea is that something soft happening somewhere should not stop something harder to happen. So hardness is a good thing, good time to evolve in. So okay, now comes something else which we need to worry about when we have more than one scattering. And that is colors. And colors is a bitch. You have, no, I'm not joking. We need to always keep track of all colors. We need to have things in the end, you have to have only color signals. So just as we always have to keep conserve energy momentum, we need to conserve color. There was zero color when the protons collided. Afterwards, there should be color signals only. Now, if you think about glue goes to glue, you can easily say if the red one here is the first one, then you will have strings or colors or cut pomerons for that matter. One configuration could look like this. So the gluon has two color charges, so you have a string going this way and this way, and this way and this way for the other gluon. Now you get another glue scattering, and you could do the same, right? Good. Color lines going here, here, here. That's fine. But we could also imagine that these color lines happens to be of the same color somewhere. So we have NC goes to infinity as the leading approximation in color, but it could very well look like this. So you have a string stretching from the proton to a gluon, to another gluon, to a proton. And in fact, if the colors allow it, this would be some kind of the preferred situation. Because if you don't do this, you will find, especially in this direction, for every multiple scattering, you will get more strings to break. You will get more pomerons cut. And that will give more multiplicity. So every time you get something semi-hard in the multiple scattering, you will also get a lot of extra soft stuff, especially not only in the remnant regions, but and that is simply not what data tells us. It was often thought of. Well, I'll come back to data. So in mind, I'm going to introduce these pictures again. So every gluon here can be thought of as a cut pomeron. It can be thought of as strings going from one end to the other. And each thing like this is then a hard scattering. Glue goes glue. And here you see all the gluons here will produce a lot of stuff everywhere. Color reconnection means that we basically have a situation like this. This is not necessarily perturbative vertices here, but there's only two colors exchange here and two colors here. And you can connect it in however you like. And this turns out to be extremely important in order to understand the soft particle production, not only in minimum bias, but also in jet physics, and where you have to worry about the underlying events. And this is the thing. I don't like this picture, but it's what people like to measure. You look at each event, you take the number of charged particles in that event, and you measure the average PT of charged particles, sorry. And you would think that, well, if all multiple scatterings were independent, then you basically get a straight line here. The PT would increase or just be the same. The average PT would be the same, but it isn't. It increases. And you see the blue line here is Pythia, which has these color reconnections. Herwig also has them. This Sherpa program here does not. So it's much flatter here. But this very weak increase tells us that all these scatterers are not independent. the reason that Pythia 6 is off is that it simply had old tune that was wrong. Never mind. So we get into a situation which is frankly quite messy, that we have to take care of all these multiple scatterings. We have to worry about how they are connected in color. We kick out a lot of stuff from the proton, mainly gluons, but sometimes you actually kick out a valence quark. And you have to worry about what does the things that go down the beam pipe look like? What does the remnant look like when you have taken lots of things out of the proton? Well, if you take out a valence quark, then you know that you can have something like a diquark on the other end. Diquarks are nice, maybe. But if you kick out two valence quarks, then you have one color going that way and one color going that way and one color going, and then we have one of these junctions we talked about before, where you take three colors out of a baryon. What is left is something that we call a junction. It also means that the baryon number, which normally would be associated with the proton going down the beam pipe, that can actually move in rapidity in a non-trivial way. Lots of things you can study here. But maybe I can pause for a while and let you ask a question. Come again? How?
So the combination of parts coming from parts technically, like showing that action, is there like some way to shoot it? Is there color to next? Depending on the person.
So what we do is to have an infinite number of colors. So every new color is new. And then afterwards we say that, well, it can't be like that, can it? So we generate the whole thing on the particle level. And if you think about strings, which we will have in the end, and all the energy that will be deposited in strings, since nature has this thing about minimizing the free energy, it will prefer to have shorter strings. What?
You break the string, but they get too long.
No, we reconnect them so that the strings becomes shorter. We can do that.
So you want that's like the gluon addition and the string basically.
Not even that. We just say, look, we have the string going to this gluon here, right? And then we have another string going to another gluon here. And we just say, but wait a minute, this one, we can actually redraw this so that this one is connected to that one. And here we only get a short stuff here.
So the string themselves, they will kind of involved that.
The strings vary color.
But you are not considering the color when we're displaying about
We are conserving the color since we have always had strings. So the strings are always color signet objects. But then how we draw the strings, if we draw it like that or like that, or that's what we can do. So we swap things around. But every swap everything will still be color signet.
Doesn't it say when you swap the string, when you have the bandage, it's all of the string by the color of the variation.
So we don't. There are ways. There are ways to do this. So there's an alternative the default color reconnection model, there's an alternative that's called QCD color reconnection, where you actually go in and assign colors. Real SU3 colors. As far as you can on each blue one, or rather dipole. We'll look at dipole, but that's easier to keep track of. And then you know that if you have two dipoles with the same color indices, then you are allowed to reconnect, right? It's still the same colors. It's just where would nature want to draw the strings when okay.
Mentioned the large scale approximation several times. So
Yeah.
if you said you actually assign the value for the city,
Well, no, we don't have to normally. I mean, we have to when we look at alpha S, for instance. Alpha S runs with something that where NC is important, and there, of course, NC is 3. But when it comes to actual colors of actual particles, we don't have to worry in the large NC here. But then, if you go to these more advanced reconnection scenario, where you actually assign colors, then you use NC equal 3 for QCD. Yeah. Yeah.
I have two observations and then two questions. One, you have spoken about the formula, but Docker in 2020 has shown strong evidence in reality discovery because the statistic is more than 5 sigma, but also for the other.
Yes.
That we see the negative parity, and this is important for the interaction scattering that I have.
Yeah.
Do you have implemented the other?
No. We haven't even implemented what we have in so we have, when we do diffractive excitation, we have a formula in there.
Only the ones.
Only the formula, because in such things, the odron would be very small.
Negative. Okay.
Magic.
And
I mean, it only comes up when you're looking at this real part of the elastic scattering. And I haven't seen anything related to the final state where you could see it. So this shows up, in very precise measurements of the elastic scattering.
okay. You understand. So, just for curiosity, because I am not an expert of this area, why for the others, what they can now say that there is a discovery, because at least the significance is greater than 5 sigma. Can you why for the formula can we say the same? Because if you do not put the formula, you will not produce it.
Well,
This is all
I don't think anyone has. So the Pomeron is there, right? It's some kind of exchange of something with vacuum quantum numbers in the same way as they have seen the model. So I don't think anyone would say that. But I don't think we ever really doubted the existence of a Pomeron. But I mean, we still haven't seen an odron in the timeline setting. It's a true hadronic state, as we have not seen a newborn.
Okay. The last question is. This was the scale. Of the variance. Then the probability distribution will take you and feel that the same form that we have shown in your first lessons, and only with the different positions around this again for curiosity, but to
Yeah.
understand qualitatively, which is the main change.
Which is the main change for what?
Then the point. Because you said that you have changed a little bit the route, the restriction of the bearings, this line.
Yes, so variance in this QCD coloring method, that really starts to be fun, because there you can have coloring connections that gives junctures, that gives variance all over the place. It doesn't work very well, but it is, many things happen there.
So it's really changed the restriction.
Yeah.
And so, let's say, qualitatively also, the distribution function, the probability distribution function is changed. You can say something like that, or still.
Yeah, I mean,
the old one.
With the QCD coloring connections, you have more bearing production, and it is also picking up some collective effects. The more multiple scatterings you have, the more probability you have to have this color reconnection that gives junctions, that gives bearings. So it depends on the multiplicity of the event and stuff like that. So it's
So the description is changed.
Yes.
The end is complicated.
yes. Yeah.
Okay.
These color reconnections, what you're doing is that you're reshuffling the configurations for those one less remaking.
That's
That's the potential energy stored in the string. Where does the energy go?
So the idea is that this is done before the strings are stretched and get their potential energy.
Okay.
So
There is no yet energy.
no, it's the strings to be wants to be as short as possible, basically. But that is true. The partons need to be separated by a Fermi before the vacuum actually starts demanding energy in the string. Otherwise, it's
So the string don't have to remain yet. What is the current configuration and preferred configuration?
well, this is the invariant mass of the things that will span the string. As simple as that. Anything else? Shall we have a break? Or is it too soon? Maybe have a coffee, yeah. Let's have a coffee.